Okay, guys, we're going to do a real brief introduction to parametric equations. You may or may not have seen these in pre-calc. What we're going to just take care of with this lesson is just how to graph them and how to eliminate a parameter, meaning change from parametric equations to our rectangular form. Now, rectangular form is what we call the way we've been graphing since Algebra 1 with our x-axis and our y-axis. Where we have a y as a function of x or x as a function of y. So that's rectangular form, and this is parametric form. So parametric equations are equations that are defined in terms of a parameter, either t or theta. They're often used to describe motion, okay, and we're going to see there's going to be a major theme of motion in this chapter. To sketch for x, you're going to solve for x and y given various values of t. So I gave you guys this first problem, example 1. Graph x equals 2 and y equals t squared minus 5t plus 4. All right. What I wanted you guys to do, and we haven't done this in a long time, but I want you to actually make a table. Okay, so pause the video, fill in the table. I'm telling you x is 2 and y is t squared minus 5t plus 4. So we're going to let t vary, okay, and we're going to see what happens to our x-coordinates and our y-coordinates. Our x-coordinates are pretty boring on this one. Our y-coordinates are mildly interesting. And for now, we're going to consider the first 6 seconds from 0 to 6. Okay, so pause the video, come back to me when you have your values filled in. Okay, so our x value is always 2, because it says x equals 2. It doesn't actually depend on a y value, on a t value, but our y coordinate depends on t, and if we plug in those different t values for y, we get these values. So when t is 0, y is 4, when t is 1, y is 0, t is 2, y is negative 2, t is 3, y is negative 2, t is 4, y is 0, t is 5, y is 4, and t is 6, y is 10. Okay, I want you to try to graph these values and see what happens. Okay, so I thought I could import a graph, but I can't for this parametric. So I'm starting at when time 0, I have the point 2, 4 on my graph. So let's just say that that's right here. Okay, and then at t equals 1, I'm down to the point 2, 0. And then at 2 equals negative 2. And then 2 equals negative 2 again. And then 2 equals 0 again. 2 equals 4 again. And then 2 equals 10. I don't know why I keep saying 2 equals. The point 2, you guys get it. Okay, so while you're plotting these points, you're getting these discrete points, but you actually have motion along this line. You started here, and you went down, and then you went back up, okay? And your result, I know mine is crooked, but is a line, okay? The thing is, though, and that's why parametrics are interesting, and if I just wanted an equation of a line, I would just say, oh, that's the line x equals 2, right? That's the line x equals 2. I don't care that it's the line x equals 2. I care that it's an object that started by moving down and then went back and moved up. Okay, what kind of objects do that? Balls do. If you drop a ball on the floor, it'll go down and then it'll bounce up. Okay, so the actual change is what's interesting, and that's why we have parametric equations, so that we can see that change. One of the things that I want to talk about is these two values right here, okay? At t equals 2 and t equals 3, you're at the same coordinate. Does that mean that if t is time in seconds, that from t equals 2 seconds to t equals 3 seconds, that your object is not moving, your ball is not moving at all? No, that's not the case, okay? There's t values between 2 and 3. T equals 2.5, t equals 2.1 seconds, t equals 2.75 seconds, all these different t values. And what's likely happening is that your object started here, went down, went beyond that negative 2, and then came back up, okay? So it went down beyond negative 2. It wasn't just a mistake the way I drew that line, and then came back up from that point. Okay, where does it happen? We'll deal with that later. On the calculator, okay, here's directions for your calculator. You're going to put your calculator in parametric mode, so hit the mode button, find parametrics. You're going to enter x1 equals and y1 equals. Instead of having just a y1 equals, you have x1 and y, so you're going to put x1 equals 2, y1 equals t squared minus 5t plus 4. Okay, while your cursor is on one of these, okay, so after you're done and you hit enter, to put them both in, you're going to arrow up and make sure your cursor is on highlighting one of those things, and you're going to hit F6 and then number 6 for path. Okay, That means when you graph it, you're going to actually get to see the path of an object instead of just the end result. To adjust a window, you're going to adjust t-values. And the t-values should be what should be the first t to plug in, what should be the last t to plug in. Right now I asked you to go from 0 to 6, okay? And the t-step, how far apart should the values be that the calculator plugs in for t, and also the x and y ranges. So I gave you all that information here for this particular problem that I would like for you to use. So go ahead, pause the video, graph it on your calculator, and come back to me. Alright guys, I was trying to import a video of me graphing on the graphing calculator. Hopefully you guys can follow my directions and you'll see an image where it looks like a little ball dropping and bouncing and coming back up. Notice that the y values do go down below -2 on that last picture. Try number 2 now. With my directions, pause the video, and I'm going to show you guys a picture of what it should look like on the calculator given my setup of what I've asked for right here. Okie dokie. Okay, so this is what the graph should look like. You should have seen the bottom half of the parabola come up before the top half of the parabola, and also I would like for you to go back into your calculator and change around those t-bounds, the t-min and the t-max. Start the t earlier, end the t earlier, end the t later, and see what happens, and you'll see that you get more or less of your parabola. But please take the time, pause the video, and go ahead and do that. For number 3, I gave you guys a new set of instructions, and when you guys are doing trig especially, because trig depends so much on the unit circle and circles in general, it's really important. You'll get a perfectly square window when x is twice your y value, which is why I gave you these for your x-min and your x-max and your y-min and your y-max. If you don't use those, they'll look different. Pause the video, graph it, and come back to me. Okay, so this is what that looks like. It should look like a perfect circle if you've used the values that I've given you. When you have it on path, which I hope you still do, and you go from 0 to 5 pi, you're going to see that you go around the circle 2.5 times. If I just went from 0 to 2 pi, okay, because if you think about how long it takes to go around a circle, you should get one circle, and play around with those t-values if you need to on your calculator so that you can see how those t-values affect how much circle you get or how many times you go around the circle. Okay, so hopefully you feel comfortable with graphing. We're going to move on to how to eliminate parameters, which means turn a parametric equation into rectangular form. Honestly, this is a pre-calc topic. There's nothing that you're going to be asked to do on AP that would do this. But to eliminate parameters, you're going to be solving for t or for theta, and sometimes when we've got trig involved, we're going to use the trig identity that cosine squared plus sine squared equals 1. And if you guys had me for AB, then you know that the relationship between that trig identity and the unit circle x squared plus y squared equals 1. Okay, in any case, so let's look at number 4. I can very easily solve for t right here. Okay, so I would say that t was 2y, and then I can make that substitution in for t in this other equation, and I have x equals 2y quantity squared minus 4, or x equals 4y squared minus 4. Okay, if you guys look back at your example 2, what we graphed, you'll recognize this parabola that was opening about the x-axis. Yes. Looking at number 5, here we have x equals cosine t and y equals sine t, so we're going to use our trig identity. So cosine t squared plus sine t squared will equal 1. And if x is cosine t, then I have x squared plus, and if y is sine t, then instead of sine squared, I have y squared. So I got x squared plus y squared equals 1, and if you look back at example 5, you see that unit circle. It really is that simple, and like I said, you're never going to be asked to do this on the AP exam. Okay, so number 6, pause, come back to me, but the easiest place to find or to solve for t is right here. So I would say that t was, subtract that 1 from both sides, y minus 1, and then I'm going to substitute this in place of t in this equation. So I have x equals y minus 1 quantity squared minus 2 times y minus 1. That's a squared, okay, and if you simplify that, you get x equals y squared minus 4y plus 3. You'd have to FOIL and combine like terms, and you get that, okay? And if you guys were to graph it in parametric form, you would see this sideways parabola. Okay, for number 7 is tricky because it's so simple. And the trick on number 7 is to see that we have an x equals sine and y is sine squared. So if x is sine and y takes that sine and squares it, then this is really y equals x squared. For any of these that we've eliminated the parameters, well, I guess you had graph 4 and 5 already, but you can go and graph 6 and 7 and see how it looks in the calculator and see that it makes sense. The last thing that I want to talk about is just to present the fact that we've been graphing sideways parabolas today, and we've never been able to graph a sideways parabola on our graphing calculator. So I just want to point out that we can use parametric mode to graph sideways parabolas or any other function for that matter by letting one variable equal t. And if it's a sideways parabola, it's better usually to let y equal t and rewrite the second with t's in place of the first. Okay, so I know that sounds a little confusing, but let y equal t and then write x in terms of what y was, except in place of all the y's you're going to have t's. So pause it, come back to me, and you'll see what it looks like. Okay, so that's what I did for here. I let y equal t, and if x was y squared and y is t, then x is now t squared. Okay, and then here if y is t, and this is what x was, I just replaced all the y's with t's, and I get this. So if you guys try graphing either of these parametric equations in your graphing calculator in parametric mode, you'll see your sideways parabolas, which is something that you weren't able to graph previously. Okay, that's really our basics for parametrics. One thing that I do want to talk about is something called cycloids. Cycloids are not on the AP exam, they're just pretty cool looking. Cycloids are curves that are traced out by a point on the circumference of a circle as the circle moves along a straight line. We have versions of cycloids. We have hypocycloids where we have a circle moving along the inside of another circle, and an epicycloid where we have a circle moving along the outside of another circle. I've got 2 examples of cycloids here that you graph them in your graphing calculator. They look cool. That's all that there is to them. They're not on the AP exam. I'm going to put a link on Schoolwires of a website where you can make cycloids just to see kind of how they function, just because they're cool looking, and if you take a college calc 2, you might be doing a little bit more with them, but really, no, they're just cool looking. So if you'd like to see a little bit more about cycloids, the link will be up on Schoolwires. Otherwise, that's all that there is to our introduction to parametrics.